Hello, everybody. In the previous lecture, we discussed the generation and recombination processes in which electrons are promoted from the valence band into the conduction band and return from the conduction band into the valence band. We have distinguished two types of generation processes, the thermal generation and non-thermal generation. Thermal generation is responsible for maintaining the equilibrium Fermi-Dirac distribution of electrons in quantum states in both bands. Thermal generation is due to the interaction between electrons and phonons. Some phonons have high energy, high enough to move the electrons, to transfer electrons from valence to the conduction band. So hence we have conduction electrons. The non-thermal generation is the one that we can switch on and off. Typically, non-thermal generation is due to light. You shine light on the semiconductor. Some of the photons have energy higher than the bandgap energy, and when those photons are absorbed, an electron-hole pair is created. And by the way, if the photon energy is below the bandgap energy, then the material is transparent for those photons. That's why glass is transparent, because the bandgap of glass, silicon oxide, is too high for photons to be absorbed. All right. Now, recombination can proceed via several different channels. The most relevant channels in the semiconductor bulk from the surface are radiative, Auger, and Shockley-Ritz-Hall recombination. Also, there is surface recombination, which follows the Shockley-Ritz-Hall mechanism, but not through the trap atoms in the semiconductor bulk, but through the electronic surface states, which act as traps and whose surface density is quite high, typically. In this lecture, we will write down the expressions for the recombination rates for the main types, radiative, Auger, and Shockley-Ritz-Hall recombination. Also, in the last lecture, we have introduced the concept of recombination time and the net recombination rate, which is the recombination rate offset relative to the thermal generation rate. So we will also find the recombination times explicitly in terms of the concentration of charge carriers in equilibrium for Auger, for radiative, and for the Shockley-Ritz-Hall mechanisms. Then I will introduce the concept of quasi-equilibrium and the concept of quasi-Fermi energy. So let us start with the radiative recombination. So radiative recombination happens when an electron meets a hole, they recombine, and the photon is produced. The frequency of such events must be proportional to the concentration of electrons. If you double the concentration of electrons, then a given hole has twice as many chances to recombine with an electron. And likewise, if you double the concentration of holes, then a given electron has twice as many chances to recombine with a hole. If you double both, then the recombination rate must quadruple. So the radiative recombination rate is proportional to the non-equilibrium product of the non-equilibrium electron and hole concentrations, N and P. The proportionality constant is called the radiative recombination coefficient. Its value varies in a broad range depending on the type of the semiconductor. In indirect bandgap semiconductors such as silicon and germanium, the radiative recombination rate is of the order of 10 to the negative 14, 10 to the negative 15 cubic centimeters per second. In the direct bandgap semiconductors, where radiative recombination is really the dominant recombination mechanism, the radiative recombination rate is of the order constant, is of the order of 10 to the negative ninth cubic centimeters per second. Now the radiative recombination constant or coefficient is measured in cubic centimeters per second due to the dimensional considerations. Due to this definition, the recombination rate, which is the number of recombination events that take place per unit time in a unit volume, is measured in inverse cubic centimeters, inverse seconds. The product NP, the product of concentrations, is measured in the centimeters to the negative 6. So the units in which the radiative recombination coefficient is measured is centimeters to the 6 times centimeters to the negative 3 times second to the negative 1, so centimeters cubic per second. Now, in addition to the recombination rate, we have discussed something which is called the net recombination rate, which is the difference between the recombination rate and the thermal generation rate. Now, thermal generation, I said earlier, happens due to the interaction between electrons in the valence band and the phonons, but also it happens due to interaction between electrons in the valence band and photons, the quants. So phonons are quanta of lattice vibrations, phonons are quanta of lattice vibrations, and photons are quanta of light. Why does that happen? In equilibrium, where do we get photons in equilibrium? So imagine a universe filled with a single crystal semiconductor. Well, just imagine. And that semiconductor is kept at a given temperature, T. So you have some conduction electrons in that semiconductor. Those conduction electrons, from time to time, recombine with the holes. Maybe the semiconductor is doped. They recombine with the holes. And some of those recombination events are radiative recombination events. So in those radiative recombination events, photons get produced. The energy of those photons is not exactly the same as the bandgap energy. It is typically slightly larger than the bandgap energy because the energy of an electron in the conduction band typically is higher than the energy at the bottom of the conduction band by something of the order of the thermal energy kT, and the energy of a hole, that is the energy of the empty state in the valence band, is typically somewhat lower than the energy at the top of the valence band by something of the order of the thermal energy kT. So when an electron and the hole recombine, the energy is released which is slightly larger than the bandgap energy by an amount which is of the order of the thermal energy kT. Okay, so now let's say a photon with the energy slightly exceeding the bandgap energy is released in the radiative recombination. Where does it go, that photon? That photon is produced in the universe filled with this semiconductor. That photon has nowhere to go. It remains in that semiconductor, and eventually this photon has a very good chance of being reabsorbed by the semiconductor. By the way, the process of photon reabsorption is an interesting effect, and it is a real effect which is crucial in solar cells, for instance, and also in light-emitting semiconductor optic devices, light-emitting diodes as well. So the photon gets reabsorbed, and when it gets reabsorbed, an electron-hole pair is produced. So when we are talking about equilibrium of electrons and photons, I mentioned phonons just because they are the first thing that comes to mind. They are the easiest to understand, but also photons are there. And in reality, in thermal equilibrium, electrons and holes are in equilibrium not only with the crystal lattice, but also with the photons, with the light which exists inside the semiconductor. All right, so this process of photon reabsorption in thermal equilibrium is a real process, and it contributes to the thermal generation rate of the electron hole pairs. Now, if we wish to express the net radiative recombination rate, we need to subtract from the actual radiative recombination rate, which is here, the radiative recombination coefficient times the product of electron and hole concentration, the value of the photon reabsorption contribution to the thermal generation rate. And that value is the radiative recombination rate in thermal equilibrium when you replace electron and hole concentrations N and P with their equilibrium values N naught and P naught. The product N naught times P naught is the intrinsic concentration squared. All right, so, and this is how you introduce the net radiative recombination rate. You subtract the product B N naught P naught from the value B and P. Now you can write, of course, express the electron, non-equilibrium electron concentration as a sum of the equilibrium value N naught and the excess electron concentration delta N, and similar for holes, equilibrium P naught plus the excess concentration delta N, and of course the excess electron and hole concentrations are the same due to the charge neutrality. Subtracting the value B N naught P naught from this product, B N naught plus delta N times P naught plus delta N, this is what you get. B N naught plus P naught plus delta N times delta N. This is the net radiative recombination rate. Now, it has the structure of delta N, the excess concentration, multiplied with something, and this something the inverse radiative recombination time. So in general, for a non-equilibrium situation where the excess concentration has arbitrary value, not necessarily negligible, as compared to the majority concentration, whatever the majority carriers are, the radiative recombination time is 1 divided by B times N naught plus P naught plus delta N, because this quantity 1 over tau radiative multiplies delta N. So the net rate is delta N divided by the recombination time. And in the equilibrium situation, the equilibrium value of the radiative recombination time is just set delta N to 0 in that expression. You get 1 over B times N naught plus P naught. And of course, in N-type semiconductors, you neglect P naught in the denominator. In P-type semiconductors, you neglect N naught in the denominator. Good. Moving on to Auger recombination. Auger recombination comes in two versions, two types: electron and hole mediated Auger recombination processes. In electron-mediated Auger recombination events, an electron and the hole recombine. This is the lab diagram here. Electron and the hole recombine. The energy and momentum released in this event are carried away by another electron in the conduction band. That electron becomes a hot one, a hot electron. Its energy now exceeds the energy at the bottom of the conduction band by something of the order of the band gap. It is extremely hot. That electron very quickly releases this extra energy of the order of the band gap energy into the lattice vibrations by producing more phonons. So this electron quickly thermalizes. We say that it thermalizes. It quickly falls down on the energy scale. It falls down to the bottom of the conduction band. The rate of electron-mediated Auger process is proportional to the square of the electron concentration and hole concentration raised to the power 1. Because the electron concentration is squared, because you need 2 electrons for electron-mediated Auger recombination to happen. So you need 2 electrons and just 1 hole. So if you double the concentration of holes, then the probability for Auger recombination doubles. But if you double the concentration of electrons, then the probability for 2 electrons to meet increases by a factor of 4. And thus the rate of the electron-mediated Auger recombination increases by a factor of 4. The proportionality constant that multiplies the product n squared p is electron Auger recombination coefficient, CE, or simply electron Auger coefficient, CE. Now you can also have hole-mediated Auger recombination, in which an electron and the hole, when they recombine, the energy released is transferred to a hole in the valence band. That hole ends up in some state below the top of the valence band by the energy of the order of the band gap energy. Now, in practice, in reality, it is an electron from somewhere deep at the bottom of the valence band which goes up, leaving a hole behind. So it is the energy of an electron in the valence band which gets higher. But you can think about holes as real particles, even though they're quasi-particles, but you can think about holes as real particles whose energy is measured downward on the energy scale. So now again, a hot hole is created in this way, and that hole is thermalizes quite quickly by giving its energy to the phonon subsystem. The rate in which hole-mediated Auger recombination takes place is proportional to the square of hole concentration, because you need 2 holes for the process, and to electron concentration raised to the power 1. The proportionality constant is called hole Auger coefficient, CH. For each type of Auger process, Auger recombination process, you can also introduce a counter process where hot electrons interact with the electrons in the valence band, and this interaction results in the production of an electron-hole pair. The hot electron loses a lot of energy, and an electron-hole pair is produced. And likewise, for hole-mediated Auger processes, you can think about a counter process, the generation process, and those generation processes contribute in thermal equilibrium. They also contribute to the thermal generation rate. So in order to figure out the net Auger recombination rate, which is denoted with the letter U, you need to subtract from the Auger rate, which depends on the excess carrier concentration delta n, you need to subtract the Auger rate in equilibrium when the excess concentration delta n is set to 0, like that. You can do this for electron-mediated Auger processes, hole-mediated Auger processes separately. You can add up the results. Now, this procedure is fairly straightforward, but the equations are a little bit long, but they are like simple equations. They are cubic polynomials. Those formulas are cubic polynomials in delta n. A cubic polynomial has plenty of terms. So just to save space, I didn't write them down in this slide. But if you evaluate the inverse derivative of the Auger recombination rate with respect to delta n at delta n goes to 0 in equilibrium, then you get Auger recombination time, and this is the final result. Now, let us consider 2 extreme cases when the semiconductor is of n-type and when it is of p-type. If the semiconductor is of n-type, then the main contributor to Auger processes is electron-mediated Auger recombination in n-type semiconductors. Why? Because when you dope a semiconductor, the typical doping level is much bigger than the intrinsic concentration. If the doping level exceeds the intrinsic concentration by only a factor of 10, this is extremely, very light doping. But if you apply this very light doping, then electron and hole concentrations will differ by a factor of 100 already because of the mass action law. If electron concentration exceeds, if it is an n-type semiconductor with the electron concentration exceeding the intrinsic concentration by 10 times, then hole concentration will be smaller than the intrinsic concentration by 10 times, so that the product N naught P naught is an intrinsic concentration squared. So even for the very light doping, the concentrations of majority and minority carriers differ by at least 100 times. But in reality, for realistic doping values, they may differ by 1,000,000 times or 1,000,000,000 times, or even more. Like sky is the limit. All right. So now let's look at this Auger recombination time for the case when the semiconductor is of n-type. For n-type semiconductors, it is the electron-mediated Auger process which dominates over the hole-mediated Auger process because it is much more likely for two electrons to meet a hole in an n-type semiconductor than for two holes to meet an electron. What should I compare it with? On campus, if you pick up two random people, then it is much more likely that those random people will be students, and much less likely than that those two random people will be professors or something like that, because there are so much more students than professors on campus. All right, so in this expression for Auger recombination time, the first term in the denominator dominates because N naught is much bigger than P naught. Also, the second term in the brackets of the first term, twice P naught, is much smaller than N naught. So the Auger recombination time will be 1 over C electron N naught squared. And likewise, for p-type semiconductors, you get the same expression for the recombination time. You just need to replace electrons with holes and electron concentration with hole concentration. So you get 1 over CH p naught squared. Good. Now let's look at the Shockley-Reed hole recombination. The theory of Shockley-Reed hole recombination is okay, it is not as complicated as, for instance, the theory of quantum gravity. It is not something that a good student won't be able to understand. But it would take an extra lecture. Going into the details of that theory would take about like one lecture time. So I decided to skip those details and present the final result instead. In Shockley-Reed hole recombination, electrons and holes recombine through traps. Traps are impurity atoms, but they are not good impurities which you add to control control electron and hole concentrations. Traps are not donors and acceptors. These are bad impurities whose energies that introduce electron energy levels somewhere in the middle of the band gap. Typically, those impurities are metals, like iron, copper, gold. I do not know what else, platinum, silver. What other metals are there? People are trying to reduce the concentration of traps to minimize it, but it cannot go to zero completely because in one way or another, metals are involved in all semiconductor processes. So some semiconductor production of semiconductor devices. So you cannot exclude those impurities completely. A trap can capture an electron from the conduction band, and it can capture a hole from the valence band. In other words, it can send the electron from that it just caught into the valence band, and this is a recombination. Then there is a reverse process in which a trap captures an electron from the valence band, and the electron that it captured from either band can go into the conduction band. The theory of Shockley-Ritz-Hall recombination is based on the detailed balance consideration among these four types of processes: electron and hole, capture, and emission. Also, it is based on the application of the Fermi-Dirac statistics to electrons which are captured by the trap, by those impurity trap atoms. The final result is presented here on this slide. It is a ratio where in the numerator you have the product of non-equilibrium electron and hole concentrations, Np, minus the equilibrium concentration product, which is N naught P naught, which is N intrinsic squared by the mass action law. And we immediately see that in thermal equilibrium, when N and P have the values N naught, P naught respectively, the product Np becomes N intrinsic squared, the numerator becomes 0, the net Shockley-Ritz-Hall recombination rate becomes 0. So this is the net recombination rate. In the denominator, you have two terms. The first term is the product of the so-called hole capture time, TH, multiplied by the sum of electron concentration N and the value N1 of the electron concentration in thermal equilibrium when the Fermi energy coincides with the energy of the trap, ET. So this is N1. The second term in the denominator is the so-called electron capture rate, electron capture time, multiplied by the sum of hole concentration P and the equilibrium hole concentration P1 in the case when the Fermi energy coincides with the trap energy, ET. Now, even though I am not going to present the derivation of this formula, I would like to consider this formula for two limiting cases: the case of low injection, that is delta N, the excess concentration delta N is much smaller than the majority concentration, and the case of high injection when delta N is much larger than the majority concentration, whatever it is. So in the low injection situation, you, in this formula, you take this formula, you write N naught plus delta N for N, P naught plus delta N for P. Okay, so yes, this is what you get. And now let us derive the Shockley-Ritz-Hall recombination time for that case. In the numerator, we already have something which is proportional to delta N. It is like what we had in the case of radiative recombination. So let's look at the radiative recombination again. So radiative recombination is the coefficient B times NP, and when we want to find the net radiative recombination rate, we need to subtract B times N naught P naught, that is B times N intrinsic squared. When you do that, np minus n intrinsic squared is this, n naught plus p naught plus delta n times delta n, as can be shown easily if you like if you use pencil and paper, or maybe you can do it in your head. So np minus n naught p naught is n naught plus p naught plus delta n times delta n. So likewise here, in the numerator of the Shockley-Reed-Hall net recombination rate, you get n naught plus p naught plus delta n times delta n. Now, since we are interested in the Shockley-Reed-Hall recombination time in the limit of low injection, that is delta n is much smaller than n naught plus p naught, that is, it is much smaller than either n naught or p naught, you can neglect delta n in the brackets in the numerator. So you get n naught plus p naught times delta n. Now the denominator, when delta n is small, the denominator becomes just tau h times n naught plus n1, n becomes n naught, p becomes p naught, so plus tau e times p naught plus p1. What happens if your semiconductor is of n-type, that is, the electron concentration is much bigger than the intrinsic concentration, which in turn is much bigger than the whole concentration in equilibrium? In that case, in the denominator, you can neglect the second term. Why? Because p naught is a small number and p1 is a small number. P naught is much smaller than the intrinsic concentration, and P1 is of the order of the intrinsic concentration. Why is P1 of the order of the intrinsic concentration? Because, let me remind you the definition of P1. It is the equilibrium concentration of holes in the case when the Fermi energy is the same as the energy of the trap. But the energy of the trap is in the middle of the band gap, somewhere. I mean, not exactly, not precisely in the middle, but somewhere in the middle. What about equilibrium concentration? What about the intrinsic concentration? Sorry, intrinsic concentration. In an intrinsic semiconductor, electron and hole concentrations in equilibrium are the same, and the Fermi energy is also somewhere in the middle of the band gap. So we can expect that P1 is not exactly the same as the intrinsic concentration. I mean, they can differ by maybe a couple of times, maybe by even an order of magnitude, but not by a whole lot, not by much. And likewise, N1, which is the equilibrium concentration of electrons, in the case when the Fermi energy coincides with the trap energy, the concentration N1 is also comparable to the intrinsic concentration N intrinsic. This means that we can neglect P naught, we can neglect P1, we can neglect N1 in the denominator. So in the denominator we have TH times N naught. Okay, again we neglect N1 and P1 because they are comparable to the intrinsic concentration. Not necessarily the same as intrinsic concentration, not necessarily less than an order of magnitude difference, but maybe one order of magnitude difference, which is not very big, which is still much smaller than the equilibrium concentration of electrons N naught. Now, in the numerator, of course, we can neglect P naught. So then this N naught and this N naught mutually cancel, and you get delta N divided by tau H. So in an N-type semiconductor, it is the whole capture process which dominates in the formation of the Shockley-Reed-Hall recombination time. The Shockley-Reed-Hall recombination time is the same, to a very good accuracy, the same as the whole capture process. And in the P-type semiconductors, you can repeat the same arguments, the same considerations, and you will find that the Shockley-Reed-Hall recombination rate is the excess concentration divided by the electron capture time in P-type semiconductors. So, okay, so the recombination time is either hole capture time or electron capture time, in N-type semiconductors and in P-type semiconductors, respectively. Now let us look at the opposite extreme of high injection, where delta N, the excess carrier concentration, greatly exceeds the majority concentration, be it electrons or holes. Well, in that case, the analysis is even simpler. Because, of course, you can neglect N1 and P1. Let's say your semiconductor is of no, you should not be looking at this formula. You should be looking at this formula. Sorry. For high injection, you are looking at this formula. So in the numerator, you have N naught plus P naught plus delta N times delta N. This is what the numerator becomes. And now you can neglect N naught plus P naught in the brackets. So you get delta N squared in the numerator. In the denominator, you get tau h times delta N. N plus N1 can be approximated with delta N. N is N naught plus delta N. Delta N is much bigger than N naught and much bigger than N1. So the first term in the denominator becomes tau h times delta N. The second term in the denominator becomes tau e times delta N. You take, well, that's because P is P naught plus delta N. P naught plus delta N plus P1 is delta N. You neglect P naught, you neglect P1 relative to delta N, because delta N is the biggest number of all three. Now you take delta N outside of the brackets. In the denominator, you get tau h plus tau e times delta N. In the numerator, you had delta N squared. So the end result is delta N divided by tau h plus tau e, like this. Shockley-Ritz-Hall recombination time in the limit of high injection is the sum of electron and hole capture times. What does it mean? In terms of the Shockley-Ritz-Hall recombination time, it means that Shockley-Ritz-Hall recombination time changes only by a factor of the order of a factor of 2. It changes from either tau e or tau h in the low injection limit to the sum tau e plus tau h in the high injection limit. So this change is maybe by 2 times, like this recombination time, this capture times tau e and tau h, they're not exactly the same, but they're comparable. But delta N, the excess carrier concentration, changes by many orders of magnitude as you go from the low to the high injection limit. That is, the effective Shockley-Ritz-Hall recombination time changes between either tau e or tau h to tau e plus tau h by a small amount when delta N changes by a huge amount. And this is why you can neglect the dependence of the Shockley-Ritz-Hall recombination time on delta N, because this dependence is very, very extremely weak. And you can approximate the Shockley-Ritz-Hall recombination time as a constant. So for this reason, if you read semiconductor papers, experimental papers that report Shockley-Ritz-Hall recombination time in a particular sample, they just report a value. Of course, you want the Shockley-Ritz-Hall recombination time to be as big as possible, so that the recombination rate is as small as possible. So now in good solar cells, where recombination, trap-assisted recombination is a crucial process that negatively affects the performance of the energy output of a solar cell, the Shockley-Ritz-Hall recombination time is of the order of maybe 10 milliseconds, 10 to the negative second, 10 to the negative 2 seconds. And that's a long time. That's a long time, really. All right, now let's talk about the effective recombination time. Of course, you can minimize the Shockley-Ritz-Hall recombination by controlling the concentration of your impurities, by minimizing the concentration of your impurities. But you cannot really reduce this impurity concentration to zero and thereby set the Shockley-Ritz-Hall recombination time to infinity. You cannot turn off, you cannot even control the radiative and Auger recombination times, so they are fixed. And in real life, all recombination channels are acting in parallel, simultaneously with each other. So in the net recombination rate, the total recombination rate is the sum of the recombination rates for all the channels which are operative. Typically, these are radiative, Auger, and Shockley-Ritz-Hall recombination, and in the recombination time approximation, that is for the low injection limit, delta n is small, much small compared to the majority concentration, you can replace those recombination rates U, R, UA, U, Shockley-Ritz-Hall with the ratio of delta n to the respective recombination time, delta n over tau radiative plus delta n over tau Auger plus delta n over tau Shockley-Ritz-Hall. Now you can combine everything together. You get delta n divided by the effective recombination time. The inverse of the effective recombination time is the sum of the inverses of the recombination times for each individual recombination process that takes place in the semiconductor, like that. It is a little bit similar to the when you have resistors. It is an analogy, right? But if you have resistors in parallel, then the effective resistance, inverse of the effective resistance, is the sum of the inverses of the resistances which are connected in parallel with each other. Now, of course, like for a parallel connection of resistors, the effective resistance is smaller than the smallest resistance found in the parallel connection. Likewise, the effective recombination time is smaller than the smallest recombination time found in the semiconductor. That is, if the fastest recombination process dominates, and the effective recombination time is the recombination time, it is slightly below the recombination time of the fastest recombination process, because the slow recombination processes simply do not have time to occur. All right, so that's how you can combine the recombination times. Now let us talk about the concept of quasi-equilibrium. Quasi-equilibrium is a situation when you have several equilibration processes. So in a semiconductor, you have several recombination processes, not recombination, sorry, scratch that. When you have several equilibration processes. Electrons in the conduction band interact with the phonons of the crystal lattice, interact with the photons which may be present in the crystal lattice, they interact with each other. So this is the equilibration, and these processes result in the equilibration of the electrons in the conduction band. Likewise, electrons in the valence band, or better to say holes in the valence band, interact with the phonons, with the photons, with each other. Resulting in their own equilibration. And finally, electrons in the conduction band interact with the holes in the valence band by means of generation-recombination processes. And in this way, electron and hole subsystems come to equilibrium with each other. Now, the equilibration processes that affect electrons only involve exchanging of very small amounts of energy between the electrons and the conduction band. Likewise, equilibration processes that affect the holes in the valence band involve exchanging very small amounts of energy between the holes and the valence band. But generation-recombination processes, interaction between electrons and the holes, involve very large amounts of energy. Now, this is of the order of the band gap energy. The band gap energy. The more energy is involved in a particular process, the less likely that process will happen. This means that the generation-recombination processes are slow processes as compared to the processes of equilibration between electrons within the electron subsystem and the processes of equilibration within the whole subsystem. Electrons come to equilibrium with other electrons much faster, and holes come to equilibrium much faster. Holes come to equilibrium with other holes much faster than electrons and holes come to equilibrium with each other. The situation when electrons are in equilibrium with other electrons, holes are in equilibrium with other holes, but electrons and holes are not in equilibrium with each other, is referred to as quasi-equilibrium. In quasi-equilibrium, now electrons and holes are coupled to the same thermal bath, which is the thermal bath of the phonons of the crystal lattice. So the electrons and the holes are characterized by the Fermi-Dirac distribution, which has the same temperature. Now, in the Fermi-Dirac distribution, you have two parameters, temperature and the chemical potential of the Fermi energy. Sorry, next slide. Temperature and the Fermi energy. So the temperature is the same for electrons and for holes. This is the electron Fermi-Dirac distribution. This is hole Fermi-Dirac distribution. The temperature is the same, but in quasi-equilibrium, the concentrations of electrons and of holes differ from the equilibrium concentrations and naught and P naught, which means that the Fermi energies of electrons and of holes are different from each other. Hence, you need to introduce two different Fermi energies, one for electrons, EF, E, and one for holes, EF, H. The quasi-equilibrium Fermi energies are called quasi-Fermi energies. Also, they are called IMREFs, even though IMREF is less standard, but the term IMREF is also used. But more standard terminology is quasi-Fermi energy. That is, Fermi energies in the quasi-equilibrium situation. Quasi in Latin means almost, not quite, right? That's the translation of quasi. And IMREF stands, the term IMREF was coined by William Shockley, and its original meaning was imaginary reference. And also, IMREF happens to be Fermi spelled backward. So if you read the last name Fermi, the name of Enrico Fermi backward, you get IMREF. Enrico Fermi was not very appreciative of this terminology. He didn't like his name to be spelled backward, so he wrote something like, I think he wrote a letter to Shockley saying that there is no need to invent new terminology when the physics is clear. So he wrote something like that. And so, yeah. Maybe we should call this energy, quasi-Fermi energy, maybe we should call them Yelkosh. Yeah, Yelkosh. I like that, Yelkosh. Shockley backward. No, we will not. We will stick to IMREFs or quasi-Fermi energies. Anyway, Okay, so we have different Fermi energies for electrons and holes. But now what are the concentrations given the Fermi-Dirac distribution? What is the concentration of electrons? What is the concentration of holes? We can follow the same derivation steps that we performed when deriving the equilibrium electron and hole concentrations as so electron concentration is the effective density of states in the conduction band multiplied with the probability for a given state at the bottom of the conduction band to be occupied by an electron. And hole equilibrium concentration is effective density of state times in the valence band times the probability for a given state at the top of the valence band to be empty. Those probabilities to be occupied for electrons and to be empty for holes are expressed as Boltzmann factors. So for electrons, it was exponential to the power negative energy at the bottom of the conduction band minus the Fermi energy divided by kT. All we need to do is to replace the Fermi energy with the IMREF, with the quasi-Fermi energy. So this is what you get for electron concentration out of equilibrium. All you need to do is to take the formula obtained for equilibrium case and replace the Fermi energy with the IMREF, electron IMREF. And for holes, it's the same thing. Take the equilibrium concentration of holes, which is NV times exponential to the power EV minus EF divided by KT, and replace EF, the Fermi energy, with the quasi-Fermi energy for holes, EFH. And multiplying the electron and the hole concentrations together, we obtain the generalized mass action law, namely N times P is NC NV times exponential to the power negative EC minus EV over KT, which is negative band gap over thermal energy KT. Now the product NC times NV times exponential minus band gap energy over KT is the intrinsic concentration squared. And intrinsic concentration squared is further multiplied by an exponential raised to the power E Fermi electron minus E Fermi hole divided by KT. So in equilibrium, when you have extra charge carriers, excess charge carriers, delta n, the electron and hole concentrations are not equilibrium concentrations. The electron and hole Fermi energies are not the same as equilibrium values. They are quasi-Fermi energies. And the factor exponential to the power E Fermi electron minus E Fermi hole over KT quantifies how far from equilibrium we are. That is, how many excess carriers you have in a unit volume. And when the system comes to equilibrium, the electron and hole quasi-Fermi energies eventually align. They first approach each other and they align. So equilibration between electron and hole subsystems is simply alignment of their Fermi energies. All right, so that's that for today. We are done with the generation-recombination processes. Next time in the next lecture, we will be discussing transport of charge carriers when you apply electric field, conductivity, also diffusion of charge carriers. Thank you all very much for your kind attention. I'll see you in the next lecture.